Hi, I'm Mena Spencer, and today I think we should grind some rocks. How about that? And make some biochar, shall we? That's what we're going to do today with 6 guys, or at least 5 guys, who do this as a regular thing. These are all agronomists or farmers or people who know their way around biochar and rock dust.
And seaweed.
Amendments to soil that make it possible to avoid using chemical fertilizers, at least as much as people have been doing, because you know the amazing thing, the dilemma we're in is that about half of the food in the world was produced only because there's fertilizer to make it, but we got to get away from using it because it's killing us. So it's a real dilemma. And so my concern right now is how we can use other materials that make it possible for us to raise as much food or more that's nutritious and that will enable us to get away from using as much or any chemical fertilizers. So I have contacted some people who have been doing this stuff. Some of them have been 20 or 30 years, been using these materials. Thomas Vanacore is in, I think, Massachusetts, is it, Tom?
Vermont.
Vermont, beg your pardon. And he owns a quarry. David Demari is in western Massachusetts, near, I guess, Northampton. Mm-hmm. And John Seaweed is
hello.
And now let me see. You're here. I'm
in Halifax, Nova Scotia.
Yeah. In Brockville is Ryan Brophy, and another person, I guess, in Massachusetts is Ted Vysotsky. Is that right, Miss?
Hello.
I guess the direction of the conversation goes back to one of your Meta's intentions to make a presentation to the Pugwash group in Canada, right? Mm-hmm. And concerning climate remediation or climate mitigation or stabilizing the climate. And you're looking for workable technologies or workable approaches to reaching that end. In other words, you want to make a presentation to the Canadian government in order to support methods and practices that are scalable and ready and can have some impact within the next 5 years.
That's true. But there's a special category too. 99% of what we have to do to handle global warming is just to reduce the emissions of fossil fuels. It's, I mean, I'm making this up. It's not exactly 99%, but it's by far the biggest thing. And there's no way of getting around that. That's the most important thing. So people focus on that entirely and don't realize or don't talk about the fact that you can actually also take carbon out of the atmosphere and put it away and lock it up. And, you know, we don't, and you can't solve the problem because you can't take enough of it out to make up for the amount we're putting in, but we can make a big dent in it. And Canada could do that if we would just pick some things that we can do to actually suck the carbon out of the atmosphere and put it away permanently or almost permanently. And that's the thing that rock dust and biochar can both do, while improving the quality of the soil. So this is, you know, that was my main concern in picking the topics that the proposals that I'm making to, I hope the Canadian Pugwash, they don't know about it yet, so you're springing a secret on them, but I hope that they will take it on as a project to try to get the Canadian government to promote these things. So, anyway.
Well, yeah, so, I mean, that's really, I mean, that's laudable and necessary. One thing that people don't understand is that in order to make a transition away from fossil fuels to renewables, and also give us time to implement conservation, emissions reductions, and things like that, the negative emissions, in other words, what you're talking about, which is to actually sequester or capture or reduce emissions from natural environments is really needed. Some people call it a carbon wedge. It actually buys us and is required to help stabilize the climate, stabilize the environment, and restore the environment at the same time. So we actually are going to have to do both. We'll have to mitigate the long-term effects of catastrophic climate change, and we're also going to have to adapt to the effects, the negative effects of catastrophic climate change, the shrinking or changing of the temperate zones. And what we're proposing with the use of rock dust, biochar, seaweed in sort of a holistic or a whole systems approach is to actually improve the environment. In other words, to do the things that you're talking about, make measurable increases in health of the soil, the water quality, the working landscape, so to speak, at the same time that we're drawing down CO2 or we're mitigating nitrous oxide emissions or other greenhouse gas emissions. And we're trying to do these things at the same time that we're deploying some of these inputs into land management, whether it's agriculture, forestry, permaculture, any other type of methods, including the shoreline. And so our proposition is really a whole systems approach where rock powders, biochar, seaweed are deployed in a land management and shoreline management, maritime restoration setting. And it solves the question of trying to do more than one thing at a time, which is actually necessary. In other words, the technological fixes that have been proposed, where they focus on just either direct capture in the air or carbon capture and sequestration, the technological fixes have shortcomings. One, because they're very difficult to scale. They're very capital intensive. Most of them are immature or untested technologies. And worst of all, they don't really interact in a whole system environment with the geotectonic cycle of the earth, which is what rock dust, biochar, land management, growing of crops and things of these nature, and forestry. These are whole systems interactions that actually can directly intervene in the carbon cycle, which is what we need to do to stabilize the climate. So rock dust by itself, biochar by itself, seaweed by itself, these things by themselves are not as important as a holistic combination put out on land, maybe to grow crops or grow trees or to stabilize and the shorelines and restore the fisheries and things like that. It's a unified strategy, negative emissions, and doing it in order to restore the environment and stabilize the climate at the same time.
And you think that all of these things can be done quicker than a lot of these other projects that are going to take 50 years?
I've been working with these things for these materials and methods for 25, almost 30 years now. Mm-hmm. And so we're not in a proof of concept phase anymore. We're actually in deployment. Ryan is probably the best person in Canada right now to actually have this discussion, because he has about 14,000 tons of suitable rock dust for remineralization and enhanced rock weathering in one location in the plains of Saskatchewan, ready to deploy with large-scale regenerative growers who understand the objectives and are also in the farming business. Mm-hmm. And Ryan has made a lot of investments of his own. We have proof of concept in terms of transport modeling and all the rest of this. And so, this is no longer theoretical. This will pay for itself over and over again, because the resiliency of the land, the increase in the crop quality and quantity, the reduction in a reliance on external synthetic fertilizers, not an abandonment necessarily right out of the gate, but moving away towards more of holistic or whole system approach to growing. These things are needed support. I think it was Greta Thunberg that said about the climate, if there's a climate emergency, it requires people to act as if there is an emergency.
Absolutely.
So we can
what we
move
need.
this. We need to move this along.
Mhm. I took out seaweed because somebody told me it's going to be too expensive, and it probably should all be used for food anyway. So I'm glad to know that you put it back in, because I was thrilled with the idea of combining seaweed with rock dust and biochar, and so it'll be interesting that we've got somebody who wants to promote that again.
Dave's actually been running a lot of calculations about how these things actually work together.
What I'm interested in is, can we make a dent? If we just show that within 5 years we can take a little bit that you could actually measure or discern somehow, I think that's worth promoting. So Dave, is it possible?
Yeah, absolutely. And thanks, Tom. That the number is just to put it on the table. The bottom line is that if you spread 10 tons of rock dust of let's say Tom's rock dust on an acre of land, you will absorb a ton of CO2 from the atmosphere in about 5 years. So that's a starting point. Now, 1 acre is 1 acre. You said there was 95 million acres in Canada. There's about 100 million tons of this rock ready to go. So you're talking 10 million tons of CO2 absorption if you spread it out over the Canadian farms. The real beauty of this, and this came out in one of my calculations runs that I did, is that there's no net cost to the farmer or to the government in doing this, because Tom's rock pays for itself. It generates enough money in extra yield and in offset to the use of limestone and trace metals, that it actually is worth more than twice the cost of the rock. So it's kind of an easy sell, if you will, toward the government, toward the Canadian government, saying, look, you do this, you're going to save 10 million tons of CO2, and it's not going to cost your farmers anything to do it. So I would place that as an argument in the first place. And rock dust and biochar are the only things that actually meet that requirement. They are potentially both carbon negative. Mm-hmm. There's no other solution out there that is really truly carbon negative. And I'll say that I looked at all your proposals, and I wrote internally quite a little report on it, which I'm willing to send to you as far as the other proposals. But solidly, rock dust is right up there at the top of the list, and it carries no risk in doing it. And I can't think of a better thing to approach the government with.
Well, the only thing the only caution I came across was it's heavy. You got to transport it, and yeah, I mean seriously. But if you have to move it too far, you've lost all the advantage, because you've put out more CO2 than you're capturing.
Well, that's not entirely true if you do it correctly. In other words, the volume proposition is what makes it cost effective and retains the carbon negative, because there's so much embedded carbon just in the silicate to carbonate reaction that you can transport it a good distance, especially if you're using volume capacity such as rail and maritime, and trying to minimize the last mile, the truck, over the road truck. But even with that, with diesel, especially if you started to work with biodiesels or electric vehicles, you could really minimize the transport costs. And we actually went to the very extent of what is possible in terms of distance bringing rock powders from one of the large resources of pulverized basalt in the United States up to Saskatchewan, Canada. We transported that material about 1,800 miles by rail, and there's still plenty of carbon left because, once you put 100 tons in a rail car and string several cars along, once that locomotive gets up to speed, it's moving under its own weight, a lot of it, and you can transport a lot of material for very reasonable cost of fuel and diesel. Now, of course, you'd like to use the material closer, and my company, Rock Dust Local, has made a business of finding regional resources for the purpose of minimizing transport. But we shouldn't use the hesitancy of moving heavy materials around as a reason not to do the right thing, because the fact is that there's very few things that are out there that would really make a big difference. And human beings have been getting pretty good at moving heavy objects. I mean, you think about maritime transport, you can put 70,000 tons of material onto a ship and put that ship, in a transatlantic or trans-Pacific crossing and really move a lot of material.
I'm thinking, though, that we would, if we actually make a pitch to the Canadian government, say this is a smart thing to do, we'd have to show them some numbers of how much to deduct for the CO2 price of moving the rock.
We can. The rock powder itself has this ability to drop CO2 and reduce nitrous oxide. However, when you put the material into biologic system, in other words, when you start growing plants and you're doing it biologically, so you're not constantly destroying the environment, but you're increasing the biologic activity in the soil through the interaction of plants and nutrients, you're actually building soil carbon, soil organic matter. And so the rock powders and the biochar, although they themselves sequester and capture material, once you put them into a biologic system, there's an orders of magnitude increase in the ability to actually draw down CO2, reduce nitrous oxide and these things through biologic means. In other words, soil organic matter, you're increasing the water holding capacity, you're actually growing plants that deposit carbon into the ground. And so you get a 5-time increase in the weathering rate, but you also get extreme benefit from this whole system approach. And I think Ryan would be a good person to talk to about this right now, because he's making very important strides towards combining biological inoculants. He's melding the synthetic fertilizers with rock powders. He's working with regenerative growers that are moving away from synthetic fertilizers and towards biologic method.
I'm a professional agronomist. I work directly with agriculturalists and farmers across Canada and different geographies. For about 10 years, we've been focusing primarily on nutrient use efficiency. So that's led us to develop new fertilizers that have multi-nutrient presentation to maximize root interception and crop uptake of these things. But it's constantly about how can we continue to do a better job of this. And it was about 3 years ago, I would say, Tom, we connected and shared a bunch of information, and I went down the proverbial rabbit hole that is enhanced rock weathering, and the different substances that are most suitable for these applications. My interest was primarily in the co-benefits to a lot of the publications that I reviewed, those being the material's capacity for soil remineralization, specifically on depleted soils that have been intensively farmed for many decades, that are lacking in many of the minerals and micronutrients required for optimum growth. But also abiotic stresses have become front and center as we encounter heat waves, drought, torrential rains, and these types of things. And many of these components, what stood out to me was silica. And this is something that we've been including into nutrient programs globally to help with these abiotic stresses, plant resilience, and so forth. And so to me, it became, how can we combine a lot of this bench testing? I love replicated trials and such, but we access, our little company directly accesses more than 300,000 acres a year with our customers presently. We're working to grow that. We have a very, very interesting group of clients. Most of those are thinking outside the box already when it comes to plant nutrition. And it provided us with an exciting opportunity to have growers that are incredibly mindful about their yields, their plant health, but also have a profound interest in the microbiome. And so we started to share some of the news that we had learned through Tom and many others regarding the benefits of pulverized rock. In our case, we started to focus on a metamorphosed basalt rock. And to us, we first had to prove the concept. And to us, that was bringing this product in large volumes, handling the material, stockpiling the material in different locations to make it accessible to these primary growers. And that's what we did. And it was not without its challenges, but it was certainly different and pretty exciting. We were able to, in the first year, deploy a variety of treatments over more than 1,200 acres of ground for growers that, were just interested in trying something different with regards to soil health, not in replace of commercial fertilizers, but in tandem with their commercial fertilizer utilization. So most of those were fall applied treatments. Predominantly to prairie soils, but in Eastern Canada as well, to offset some of the calcitic and dolomitic lime applications for pH amendment. In the prairies, we were looking more so at remineralization potential with nitrous oxide emission reduction and carbon capture kind of on the back burner, until we're able to confidently speak about there being an algorithm that is universally accepted and in place, such that growers that utilize these type of technologies can be credited on a per acre or hectare basis. We opted to focus on the agronomics and the benefits of using these types of.
Yeah, well, I want to stop you about, because I want you to clarify for me about this nitrous oxide. You mentioned it, and I know that one of the disadvantages of fertilizer is that it releases this laughing gas into the atmosphere, and it's very harmful. It's a greenhouse gas, a serious one.
For
so now how do you, which of these amendments does the job of avoiding that? Because you're saying that you want to see some of these things put in as a substitute for some of the chemicals, if I'm not mistaken, in synthetic fertilizer, but you're not going to abolish the whole kit and caboodle of chemical synthetic fertilizer. Is that right?
That's correct. Yeah. And a lot of that comes back down to microbial health. Whereas the pulverized basalt, for instance, becomes a source of nutrition for soil microbes. Those soil microbes enhance the plant's ability to more effectively utilize the nutrients available in that soil solution, but it also helps to mitigate nitrous oxide emission from that system. In agriculture, we typically measure nitrogen loss as volatilization, and this has become critically important, especially as the price of nitrogen fertilizer inputs continues to increase. Most of these treatments are chemical in nature. Many of them are detrimental to microbial health in the soil solution. So we're very actively looking at alternatives to replace these chemical additives that enhance microbial health rather than destroy it, essentially.
Okay,
And,
I want to make sure that I understand something. Now, I imagine that the most important thing is that the nutrients, the reason for wanting fertilizer is you really got to get more nitrogen in the soil for a lot of crops to flourish. And now you want to, but we don't want to keep putting nitrogen in for a whole lot of reasons. But if you put in nitrogen in the form of some of these other things, like I assume seaweed or some other organic fertilizers, it's not as detrimental and it doesn't escape as much, or what? Get me clear on why, what we should be trying to use instead of what we're now using, and in just for the nitrogen part.
Sure. And that comes down to nutrient management. So typically crops are fed to achieve their yield potential or their yield goal. So in the instance of urea fertilizer, under the right conditions, you can have almost 100% efficacy of utilization of that nitrogen applied. In other instances where you'll have humid conditions or wet soil, you can lose up to 44 or more percent of that total N to ammonia volatilization within 24 to 48 hours post
Where it
application.
escapes into the atmosphere and does its bad things, right?
Yeah, absolutely.
And
But it also can leach in the form of nitrate, but it can also get tied up in the soil essentially through a process called denitrification. So all of these factors make it such that that target plant does not have access to these important resources to realize its yield objective. So by adjusting the means by which we apply these nitrogenous fertilizers and combining them with other ingredients, such as those that we listed previously, make them more available to the microbiome, but also the plant itself. And as such, they aren't lost to the atmosphere, the water table, or simply.
So what does that? Is it the biochar that hangs on to the nitrogen and makes it more efficient? Or is it the rock dust, or both, or neither, or how do we do that?
Meta, let me interject something here. That's kind of my area. It's the alkalinity of the rock dust that really helps the bacteria in the soil to be in the form that can handle the nitrogen efficiently. If you get acidic, which most of the soils in eastern Canada and certainly New England are very acidic, that favors the nitrous oxide production out of the soil. Now, all the rock dusts that you work with, like the stuff that Ryan has up in Canada, it has latent alkalinity to it. In fact, that's part of the carbon dioxide absorption mechanism, is the alkalinity that's in there. It's a silicate alkalinity, and that actually serves to stabilize the soil, as Ryan was saying, and prevent the release of the nitrous oxide. So it does have the rock dust does have a lot to do with how much nitrogen gets released or volatilized or wasted. And because the rock dust will support the biological community that can process the nitrogen source effectively.
Okay, thank you. Now, what kind of rocks do you need to use? Because I think I've read that not everything's equally good. Obviously.
That's actually it. There's a cross section of a rock that can be used. Basalt, I think that stuff Ryan has is a meta basalt. Am I correct on that?
Right, that's the Blue Ridge.
Blue Ridge. Okay, well that's got a pretty good carbon absorption on its own. There's some other basalts around here, Pioneer Valley basalt, that is actually not quite as good at carbon absorption, but it has a good amount of trace minerals in it. The black rock that we were calling black lime that Tom was working with, that has an interesting combination of both short-term and long-term alkalinity, a lot of trace metals for remediation, and it absorbs about 200 pounds of carbon dioxide per ton. So as it converts over from silicate silicate to carbonate. So most rocks have.
Yeah, I think you were really enthusiastic about that black rock, right? It's a kind of shale.
I do.
Uh-huh.
It is. I'll let Tom go into this a little bit, but it's an interesting mix of plant life from the Ordovician era,
Yeah, that's right.
and it has a certain amount of free short-term alkalinity and long-term alkalinity, which is really good for plants, and absorbs carbon. So, Tom, if you want to expound on the black rock a little bit, it might be good.
Sure. What we call the quarry down near us in St. George Black, the St. George Black lime. It's part of there's a couple of economic supplies in Vermont, one by us and up near the border in Swanton, Vermont. It's a very, very old deposit of a very deep sea deposit originally, at a time and in a condition that was basically anaerobic. So the reason it's black is because there's actually carbon in it, and it wasn't releasing carbon to the atmosphere or to the water. And as such, when you bring it to the surface in quarrying, as an example, it's the first time that it's seen daylight, and those materials have seen daylight for about 425 million years. And it begins to weather and react in the open quite rapidly. And as a result, all of those nutrients are in a very, very fine matrix. There are some crystals in there. There's sulfur compounds. There's elemental carbon in there, and they provide a tremendous amount of nutrient and exchange sites, alkalinity for growing plants. And besides having this carbon capture potential, can provide buffering action to soils and acidic soils, which is very important now, especially with wildfire production, throwing a lot of dust into the air and ash into the air that then turns into a acid rain. These sorts of materials are very, what I call functional minerals. And so Ryan has been working with this material in Eastern Canada for about 2 years.
Now, wait a minute, Ryan, you've got a whole pile of rock dust ready to roll, but does it include any of this black stuff?
It does indeed, and I've been introducing it. We've done several field trials. It was deployed on about 2,000 acres here in Eastern Ontario as a value-added filler for conventional bulk blended fertilizers, but also pH amendment with the remineralization potential. So we've been working with it for a couple years, and we have several tons on hand here as well.
Now, I've read that there's more research needed to specify the speed with which this the CO2 is taken up. I'm not sure. I mean, I got the impression from what Tom just said that you already know how quickly it's going to be taking the carbon out of the atmosphere. But I didn't know that. Is that the case? Do we know how quickly you can count on the carbon in for most rock dust absorbing the CO2?
Meta, let me comment on that if I could. There's been a lot of studies, especially recently, on that subject. They're looking at ground up granite. They're looking at rocks like we're working with here, the basalts. The consensus is that it depends on the particle size of the rock. In other words, how finely ground is it, and the friability. Now, the reason I gravitate toward the black rock is that it's very friable. You put it on the ground, even chunks of it break up fairly readily because it's not consolidated very strongly, and it's got a soluble portion that kind of rinses out right away, and it leaves a porous like structure behind it that then the ice gets in it and breaks it up and all that good stuff. So some of the rock, especially the fine stuff like we're talking about, the 100 million tons of tailings that are too fine for use in quarries and things like that, that stuff breaks down rapidly. And there's a fair amount of scientific research quantifying that. So we can actually say that the finer grades of the rock dust will act within the 5-year period. In fact, there's evidence of some of them acting as fast as 40% a year in the fine grades.
Mhm.
The other thing to keep in mind is that once you put these materials into a biologic system, in other words, where there's plant nutrient interaction, the actual presence of the plants themselves and the microbial activity around the roots of the plants particularly will increase the weathering rate by sometimes 5 to 10 times the rate of just the dissolution or the chemical dissolution rate of rock alone. That's why we keep saying and stressing the whole system approach is the better one. When you put biochar in with rock dust, you get carbon capture, but you also get carbon architecture for microbial populations. When you put rock dust with plants, you get the microbial plant nutrient interaction that enhances the entire factor. So it's not just the rock itself or the biochar itself. And if you wanted to segue into seaweed, this is a good time to do it, because seaweed, besides connecting the terrestrial applications of rock dust and biochar to the shoreline communities, which is something we need to do. And actually, if you look at enhanced rock weathering, part of the reason that we're doing this is to increase the alkalinity of the oceans. In other words, the cations, the base cations, the buffering action will go down to the ocean and ultimately help raise the pH of the ocean, which is necessary for climate mitigation. But going the other way, taking seaweed, bringing the seaweed or seaweed extracts back to land, these are very, very powerful biostimulants, plant growth regulators. They're totally natural. They provide a lot of trace nutrients, but also very specific hormones that are naturally occurring that are beneficial to both plants and animals, and including humans. And so maybe John could talk a little bit about the whole environment that seaweed is produced in, that the potential of a seaweed farming and harvesting, increasing the harvesting of the seaweed along the shorelines for shoreline restoration.
Well, I guess when you said you're from Halifax, I figured you're the seaweed man, right?
Well, it's not on my business card, but that's my component here. Just to go back and touch on a few points on this. So my background has been in seaweed. I worked for one of the larger independent seaweed companies in the world for 10 years. And yeah, we sold everything from human food applications to livestock, natural health supplements, and of course, crop input products. On the crop input side, and Tom touched on it, there's a biostimulant liquid, and there's also soil application. And on the soil side, to get back to some of the Ryan's comment, a seaweed in the soil plays many roles, and it potentially can differ based on the type of seaweed, because you have browns, you have red seaweeds, you have green seaweeds. Biologically, they are different. So there's some learning to be had in terms of which ones provide the best results in several areas. One area, obviously, it's organic matter. It's, when it goes into the soil, it decomposes. So it's organic matter to the farm. In that decomposition, you're releasing biological compounds and active ingredients that stimulate that root environment. It enhances the ability of the microbes and the bacteria in the soil to break down what's there and allow that material then to be uptaken by the roots as nutrition, and even to enhance water efficiency, the drawing in of water from the soil. So you have that happening. And with that, you are also then increasing the rate of growth and the quality of the crop, which has a return on investment for the farmer. So all of these components go into the soil. The seaweed has a synergistic benefit in actually breaking those constituents down, enhancing the growth of the plant, which returns an economic value to the farmer. And these products have been sold globally by dozens of companies over hundreds of countries, with lots of proven scientific reports out there, published, peer-reviewed, demonstrating the biological effect of seaweeds in crop production, both in soil and in foliar application.
Okay, now here's where I got hung up, because I was enthusiastic about taking the seaweed out. Not only, of course, does it provide the right nutrients to the soil, but I thought, well, look, if you take the seaweed out, it absorbs more CO2 from the atmosphere than trees do, apparently. And if you could make it into biochar, then you would have the biochar that you could sequester, and this would be as good as, the other forms of biochar, which is really carbon negative. But of course, if you make biochar out of seaweed, it actually all the nitrogen escapes, so you don't have the nutrient value in the biochar that you would have had if you just applied the seaweed to the soil. Right. Or maybe, I guess the other alternative is make it into an extract. I think they make liquid extracts, but that's still, that CO2 is going to go back into the atmosphere. So, you don't really have any advantage over using any other form of organic fertilizer, do you?
Well, it's not, I would never call seaweed a fertilizer. It's a biostimulant. It's an organic matter. It does have active compounds, cytokinins, auxins, gibberellins. They are present, and these actives interact with the rhizosphere around the roots and the minerals and nutrients there. I would be reluctant to say you would want to make a biochar of seaweed, because I'm not sure your CO2 footprint would favor that application.
I've been told
I would take raw material.
Wrong on that assumption. But what I'm thinking is we're going to probably have we're proposing another project that would take place around Hudson Bay. Hudson Bay is apparently just crawling with seaweed now. All of a sudden, I don't know why. They're full of seaweed. Is there any way of creating jobs for those Inuit people around the border who could harvest some of that stuff? Yeah. And it's so far away. The transportation and the processing and everything would be just prohibitive, I think. Is there? Well, there's a number. Ideas?
Yeah, well, there's a number of options there. I'm from originally Prince Edward Island, which used to have a very substantial seaweed harvesting industry of Irish moss. It was used for the food industry, but an invasive species took out that crop. And what you're having now is climate change is affecting oceans in terms of pH, temperature, etc. And different crops, they're moving around. So my guess is if Hudson Bay all of a sudden, I don't know if this is the case, but if it has a bloom of more growth, it may have now become a temperature and environment and a pH very suitable for faster growth of an indigenous species. So that biomass, if it is growing, and you can determine, and this is important to do this, understand what portion of that biomass you can take out every year so as not to negatively affect the environmental and the ecological footprint of that area. So if you can establish that, take that material out, you probably have enough photo period length in the summer months to passively solar dry it. It's done extensively in Japan on rocks. On rocky shorelines, they take their kombu, they lay it out, they let the sun dry it to about a 15% moisture, and now it's stable. And then that material could be coarsely ground up for bulk density purposes and transported en masse to wherever you needed to put it. So there is an option there. That same approach is being done a little differently in Eastern Canada, Eastern US, where people are looking to grow seaweed on ropes, cultivated seaweed, as a cash crop for some farmers. Same idea. Grow it, dry it, hopefully passively with the photo period that we have in the summertime, because most of those seaweeds are actually harvested in June, July. So it's a great time to dry it. And then that becomes a biological biomass for applications such as ours.
Now, I was also told, though, that there's, you don't want to waste your food value on putting it in the soil. that is
Mhm.
more valuable for people to eat. I don't know. What do you think of that?
Well, yeah, absolutely. I ate a lot of seaweed in my travels to Japan, and it's a very significant part of that cultural diet. But the amount of seaweed that we could grow, given the coastline size and the number of lines of ropes we could have, in far exceeds what we physically will consume. It's just not in our culture. I already know now in Nova Scotia, there's some work being done that they could generate 2 or 3 million tons of seaweed from those farms. Well, that would last for Canada for how many years? So as a culture, we're not there yet. We can grow far more than we will ever consume as food or as a food ingredient. That'll happen over time, but in the interim, the sky's the limit, up to the point where we need to understand the ecological impact of large seaweed farms in the various bays and inlets, because now you're entering into that space a plant that's going to absorb nutrients. So you got to monitor that. You can't overpopulate a bay. I see that happening with mussel farms in certain areas in the maritime provinces, where bays almost become nutrient deficient, and the mussels hardly grow because there's not enough nutrient in that water. Seaweed will have an impact like that, much less so, but it needs to be monitored and ensure that you're not
Wait
being
a
a
minute, you're
negative
saying,
impact.
I beg your pardon, you're saying that seaweed is going to take up the nutrients. I was hoping the seaweed was going to create nutrients for the shellfish, no?
It does. I mean, you look at integrated multi-trophic aquaculture, you can actually, in that environment, seaweeds will absorb microscopic components of salmon waste and biofilter the water. They are absorbing things out of the water to grow. They are bioaccumulators. I know when I was selling this material into the US natural health supplement market, one of the species we looked at, we had to be careful from which area we harvested because it had a higher arsenic level than another area. Seaweed is a bellwether for that body of water. It represents the composition of the minerals, the constituents in that water. So it does absorb nutrients. It does absorb things from the ocean, and you need to make sure when you're growing seaweed in large scale, you are not negatively impacting the ecosystem that everything else is growing in.
Well, this other guy, Brian von Hertzen, is putting up the farms in the ocean, in the Pacific. And he brings up, he has pumps that bring up water from deeper levels of the ocean where the nutrients have sunk, and he brings it up for the seaweed to absorb. And then he says all the fish come and just have a great ball. They have a banquet.
If you look at, and it's definitely done in smaller scale across Northern European countries. It's being done on the west coast of Canada. It's being done on the east coast of US and Canada. When you look at reasonably sized farms, they are doing some very positive things in terms of creating enhanced environments for ocean life. They are reducing the temperature of the water because you're creating a shade with a canopy. You're lowering the pH of the water. You're doing some positive things. But some of the farms that are being proposed, like on the northern coast of Holland and Denmark, that are going to be attached to their wind farms, are going to be a massive scale. And there was even one, I read a report when I traveled to Japan, some scientists wanted to put like a 25 square kilometer sea farm out in the ocean to grow seaweed as a biofuel. It could never be engineered to physically exist there and not be destroyed by currents and the waves. But that amount of seaweed is absorbing also out of a space something that was there. And I'm always concerned about, as human beings, we go in think we can just do this very quickly and have no impact. Like some people are talking about taking millions of tons of seaweed and sinking it to the deep ocean floor. I don't know what the long-term impact of doing that would be. I would rather look at that biomass and say, what could we do with that for us to eat, for us to feed our livestock
I know
and
that
maybe
Brian,
reduce methane?
I know, I talked to him about it. Brian Van Hutsen is not going to sink it on purpose. He's trying to capture it and use it for various things like food. But he says that as you grow it on these ropes, that about 25% of the stuff does fall off and it sinks to the bottom. And he figures that that's how much they are sequestering. You can count as it goes to the bottom, it stays there. So, you can count that as, against the whole notion of taking air, carbon out of the atmosphere. But it isn't that he's deliberately sending it to the bottom. It's that 25% of it's going to fall off naturally.
Yeah. And it all will fall off because seaweed's fluff. That seaweed is seasonal. And so it will disintegrate on the rope if you leave it there till August, September, October. The rope will be bare. So you grow it like a crop, you harvest it as a crop, and then you utilize it. And I would recommend not, harvesting it sooner than later.
Good. Okay, I want to turn to biochar because that was my favorite thing a couple of years ago, and it's not been discussed as much in this conversation. But I'm just very aware that it can do great things. I don't know who wants to speak to the bio. We had a conversation with Ted before the thing started, in which Ted showed me a photo of a big cornstalk that had been raised in a foot deep soil, but it had biochar in it. So show us that corn. Now, let me see if I can say something so the camera will go to you, Ted.
This is the biochar that's grown in the urban gardens in the back streets of Boston. That's 1 foot of soil.
Pick it up.
I can't see because
Pick it up a little bit. There you go.
I'm trying to
Oh, it's about 10 feet tall, isn't it?
That one was 14 and a half feet tall. If you notice the guy's arm, it's the same thickness as the base.
Yeah.
And basically, we've got it as high as 22 feet tall. It produces several ears of corn, and it's wind resistant. It doesn't pull out, and it has some extra properties that I think the University of Mexico and Frank Jeffers has decided to acclimate it to the northern climates. So we have a test plot in Belchertown that we've been doing since 2011.
Yeah.
And,
now, you're part of the glory goes to the genes or something, and the genetics of the thing, and part of the glory goes to biochar. Is that right? So whom shall we credit the most of this miraculous growth?
I would think the combination of everything that we've learned together, and we had to prove it out to show that rock dust and biochar and all these amendments had a positive impact. And after all these years, we found the secondary benefits in the past 4 or 5 years. Bottom line is that we can grow food anywhere and to meet the needs. However, business as usual is going to not do it. I've done biochar in poor soils with seaweed in a project that we recovered in Godbout in northern Canada. And that was on the shoreline project to recover the erosion that had caused 3 streets to wash away into the abyss, because we sit on the edge of the glacial ravine. Now,
excuse me, I'm curious. You mix all 3 of these ingredients together, is that right? You
Yes.
mix the biochar, some rock dust and some seaweed, or maybe something else too. You put it all together and then you put it in the soil. You don't just sprinkle it on top. You insert it in grooves or something.
Since it's all glacial sand and does not hold water, the rock dust was coarse, basically. So we didn't have to add rock dust, but we did use some of the sea minerals that were around there. And it was in the form of marine clay. And my friends were potters, so I had plenty of time to play with that stuff. And yes, we tried every experiment in the book, and it worked. And the mayor gave us $500 to recover the whole thing. So we had 10 volunteers, 3 research scientists, 2 technicians, and a bunch of engineers all pitch in, and we recovered it.
Okay, now let me ask him in general, all of you're basically in favor of, if you could put all these 3 ingredients together, that would be good. Apart from the things like transportation and the cost and whether or not it's a wasteful use of the materials that should be eaten, or all these other considerations, if you could just have your pick of all these 3 ingredients and put them together, how would you use it? Would you mix them together? In what proportions? Yes. And then you'd put them in the soil, or would you put it on top of the soil, or would you put it on some of it in a spray can and spray it on the plants? I want to know how to use this stuff.
Dave?
Tom, that's your game. I think you're doing it now.
Yeah, well, it's going to have to do with where is it going. I mean, you could prescribe, we put these materials together in certain proportions and we put it out on the land. But of course, that sounds like an academic exercise. Until you know where the material is going and in what use, you really can't answer that question. As an example, Ryan is interacting with a lot of very large scale growers in Saskatchewan. They're going to have their own particular way of adopting these materials into their growing environments, and the physical method of application is also going to figure in. So getting back to what I do on every day on a daily basis, I mean, I just came from the quarry today. We were actually getting ready to blend rock dust with biochar in a particular formulation that is generally used as a material that's incorporated into growing media, whether that's permaculture raised beds that are being built, or whether that's potting soils, whether that's greenhouse growing, whether that's tillage, applied to the ground and incorporated through various methods of tillage. We tend to put those 2 materials together if we can, and we'll use different proportions depending upon what they're trying to do. We would use seaweed, raw seaweed powder in a minor percentage depending upon where it's going, and ultimately interaction with plants in the root zone would be the most effective. But the material can be broadcast to the surface and in a place where plants are growing, and would do very well in the plant nutrient interaction. So to answer the question, there wouldn't be just one formulation. It really has to do with where is it going, how's it going to be used. Mm-hmm. I'll give you another example. Establishing a permaculture from desert. In other words, if you were going to take an area that was basically turning into a desert and start bringing it back into a habitable temperate zone, you might take these materials and put them in the root zone of your successional planting. If you're going to put a tree in there, as an example, if you have an idea that you're going to plant many trees, well, in the hole that the tree is going to be put into, whether it's a little hole or a big hole, taking these materials, the three materials together in the proper proportion, putting them in the hole and putting the tree in that hole will increase the likelihood of that tree not only to survive, but to thrive.
Mhm.
And so that would be a beneficial use. So, and it's ultimately doable. In other words, you don't need to have a degree in engineering to understand how this works.
Mhm.
But you have these materials and you put them in a hole and you have a shovel and a pick and shovel and put the tree in and make sure you water it. You know, your likelihood of success is a lot greater than if you hadn't done that. Now, if you're a big farmer and you've got a 20,000 acres that you're taking care of, you're going to be talking to that farmer and saying, what are you doing? How can we integrate these materials with what you're already doing? Because the last thing you want to do is create more work for the farmer because they're going dark to dark as it is. So this is a question of integration. And that's why what Ryan is doing is absolutely brilliant, because he's actually taking these principles and he's building formulations and building mechanisms to get these materials into, especially into transitional growers who are now moving in the direction of land restoration.
Well, how do we get this to happen? In terms of, do we need to persuade somebody in government? If so, does Ryan have their ear already? Should we try to send Ryan to talk to Trudeau, or what shall we do? How are we going to get this to happen most politically effectively?
Well, we thought you were going to do that, Meta.
I'm happy to do it, but I want to know what I'm doing, you know? I mean, I don't want to make a mistake. And if somebody else is doing a better job of it, I don't want to waste my time on it.
Well,
So-
I think, well, Ryan can speak to it, but I think the important thing is to demonstrate, to show, it's a show and tell, to show that these things are being done right now, that they're scalable, that they're in need of funding because of the time frame. In other words, there's an urgency. We're not going with our hat in our hand to say, you know, we're going to need funding forever. What we're saying is, if you want to scale this rapidly, you want to do something important in the next 5 years.
I don't know whether it'd work. Get Parliament to say, we have a new law that everybody manufacturing chemical fertilizers has to include 20% rock dust and 20% biochar and 5% seaweed in it. And then you can sell it. Otherwise, it's illegal to sell it.
Well, okay, that's one way of doing it, but the political problem that we're in now is that it appears, to me anyway, that the political parties have decided that it's better to disagree for their own purposes than to agree on anything. So to ask the politicians to do anything where they've got their own interests to defend is probably a recipe for failure, because the gridlock is the order of the day. However, the idea that you're going to help a farmer or help a grower or help a forester or help a fisherman or help individuals actually succeed and enable them and empower them to be the frontline workers that they already are in mitigating catastrophic climate change, that will cross party lines. That's going to be a hard thing to assault, whether you're on the left or you're on the right of the political spectrum.
Well, that's why I've been thinking in terms of, can you show me how a particular Inuit, a fisherman can make a little extra money by doing seaweed? Or can you show me how, the farmer who mixes in some rock dust is actually going to benefit, and will, then we just try to get him to do it. That's another matter.
It's the whole system approach. That's the Nexus model. It's negative emissions in a unified strategy equals drawdown. And the government is not giving a handout. These are not handouts. I mean, you're looking at actually interacting with the thermodynamic imperative of satisfying, climate mitigation. You actually have to integrate with the natural system. So you can point to any natural system and say, these inputs will do these things. these things are helpful for individuals to succeed in mitigating, in satisfying, given a food security and the rest. So you give them a whole system approach and allow them to decide how they're going to support it.
Well, okay, now all of you guys basically agree. I haven't heard any of you contradict anybody else, but maybe you do in private. But if you're all on the same page, then that's a big help to me, because I want to make sure I'm not really saying and doing promoting something that one of you is going to think is crackpot. But you're not. None of you is a crackpot, and I think you're all sort of in harmony, aren't you? So let's go for it, shall we?
Yes, absolutely.
Yes.
Sure.
All right, great. Thank you. It's wonderful. Thank you. It's been a treat and a real privilege. And I'm probably going to use your brains some more before I'm through with you. Okay. Thanks. Have a great
Thank
day.
you.
Thanks,
Thank you
Rhonda.
very much.
Bye.
Appreciate it.
Bye-bye.
Take care.
Project Save the World produces 2 of these shows each week. This is episode 497. Watch or listen to them as audio podcasts on our website, tosavetheworld.ca. People share information there about 6 global issues, and to find a particular talk show, you can enter its title or episode number in the search bar, or the name of one of the guest speakers. Project Save the World also produces a quarterly online publication, Peace Magazine. You can subscribe for $20 Canadian per year. Just go to pressreader.com on your browser, and in the search bar, enter the word peace. You'll see buttons to click to subscribe.